Good morning, everybody. This is Carl Griffith from Graybar, and I want to welcome you all to our G2 Talk webinar series today. Today's topic will be considerations for planning optimum data center cooling, and we're really looking forward to it. This is a great presentation. I've had the opportunity to review it just a little bit ago, and it's fantastic. Before we get started, I wanted to give you a little bit of information about Graybar. Our mission statement's online here, that we want to help our customers power and network and secure their facilities with speed, intelligence, and efficiency. And in this particular case, the facility is a data center. Graybar is a distributor that can help you if you're building a data center or redesigning or rebuilding a data center. We're here to lend a hand. We can provide materials that have to do with electrical or communications connectivity, cooling, lighting, security, automation. All of those elements in the data center construction or rebuild are available from Graybar. We'd like to work with you and your associates in any project that you might have. Before we get started here, I wanted to remind everybody that the first 50 people that came up online and stay with us on this presentation will get a gift certificate for a cup of coffee from a national coffee retailer. Watch your email in basket, and you'll see an email that'll come in with the instructions on how to exchange that email for a cup of coffee. I wanted to remind everybody that this presentation will be archived on graybar.com, so if you want to go back and get the data that's off this presentation, you can by visiting graybar.com. There's also a white paper that accompanies this presentation, and you can get some more information about this topic from the white paper as well. Just go to graybar.com and look for the white paper associated with this presentation. Our presenter today is Ian Seaton from Chatsworth Products. Ian is a friend of mine. He and I have been traveling around the country and meet each other and making presentations around the country about data centers. Ian participates with the Green Grid and ASHRAE. He's a subject matter expert when it comes to cooling and efficiencies inside data centers. So without delaying the presentation at all, I would like to turn it over to Ian. Thank you very much, Ian, for joining us today.
Thank you, Carl, for that kind introduction. Today we'll be talking about optimum data center cooling and a quick definition of that. By optimum data center cooling, we mean both effectively delivering enough cooling to every piece of IT equipment in that space and also efficiently doing it for the lowest possible cost for that space. And the other part of the presentation title is Considerations, and that's not a detailed how-to recipe on building this whole plan. But today I will hopefully be giving you some considerations that would go into your development of such a plan and providing some suggestions on resources and some things to be sure that you don't leave out of your planning for developing such a plan. We'll start with a quick review of the ASHRAE environmental guidelines and the benefits of airflow containment and containment variations before we get into the meat of the presentation on considerations and finally suggestions on total cost of ownership and how to do that analysis. So I'm thinking by now everybody on this call should be very well familiar with the 2008 revision to the ASHRAE environmental guidelines for server inlet temperatures, which expanded that envelope, dropping the bottom end down to 64 degrees, raising the upper end up to 80.6 degrees, and changing our humidity management from a relative humidity bogey to a dew point bogey with a 60% maximum on the relative humidity. And that guideline was revised again in 2011 with another white paper, which did not change the recommended envelope, but did make a couple of important corrections to the 2008 paper. The first one being, in 2008, we said that you could operate in the allowable range for a short period of time without giving any guidance on what the definition of short was. So that's been corrected with the 2011 paper, which provides tables and equations that allow you for your area to make a calculation on what will be the reliability impact on your equipment to operate at different temperatures from what we call the X factor temperature, which is a 24/7 at 68 degrees. We'll talk a little bit more about that towards the end of the presentation and what the impact of that is. And for the Celsius challenge, we can look at this chart here and see the second correction to that first paper was breaking out the Class 1 servers into 4 subcategories, the A1 through A4. A1 with an allowable operating temperature of 59 to 90 degrees, A2 from 50 to 95 degrees, A3 from 41 to 104 degrees, and A4 from 41 to 113 degrees. Realizing that any servers you buy today are probably going to fall into that A2 group. Legacy equipment that you may have gathering dust in the back corners of your data center is probably going to be an A1 server, just to kind of put this into perspective of what you might be able to do with some of the temperature management and manipulation things we'll be talking about today. Next, I want to just briefly touch on containment, because that is going to be the foundation for being able to achieve everything that's talked about in the TCO development. I suspect by now most folks on this call are going to be familiar with most of these 8 benefits that are derived from containment. If there's any uncertainty or mystery associated with any of these elements, they're covered in great detail in the white paper that Carl mentioned, how much containment is enough, which can be downloaded from the registration page on the Graybar website where you registered for this seminar. So that's available as some backup information for what we'll be talking about. And with containment, we're talking about 3 basic variations of containment: hot aisle containment, cold aisle containment, and cabinet containment. Cabinet containment being basically just a variation of hot aisle containment, but with individual chimneys for each cabinet rather than a combined chimney for the entire contained space. And with there being 3 different types of containment that are available in the marketplace, there's been an ongoing debate about which containment is going to be the best containment for me. And the efficiency part of that argument has finally been settled by a third-party research project conducted by Intel and T-Systems in a data center research lab in Europe. And the title of their paper, where they reported their results, basically gives the answer to that question. Containment is containment, and they're all more or less equal in terms of the efficiency impact on the operation of the data center. That paper is available at the www.datacenter2020.com website, and because we'll be talking about a couple other items that were developed out of that study, and that may be of interest to folks. So if efficiency is not going to be the determiner of what type of containment we're going to choose, what do we base our decisions on? And that gets us into the first part of the discussion on considerations here. So we'll look first at hot aisle containment and what some of those considerations might be. First, hot aisle containment is typically going to be the easiest to integrate with fire suppression systems. The barriers from hot aisle containment are going to abut the surfaces where fire suppression is deployed, creating some separate rooms into which that fire suppression will deliver. If we're on 10-foot centers on our fire suppression pipes, you can probably get 4 or 5 rows of cabinets before you might start facing a clearance issue and have to move those rows. If we're on 8-foot centers on our fire suppression, then it's a non-issue and everything will work just fine. With hot aisle containment, you are creating a hot work environment for any work that needs to be done in that space. With hot aisle containment, we can use a raised floor for air delivery, but we don't need it, so we can take advantage of other architectural features of the building in terms of overhead delivery for free air economizers or fan wall delivery for other economizer systems, and that's all compatible with hot aisle containment. The Intel T-System study also looked at ride time, which is how long servers will run before they start shutting down after a cooling equipment failure. And they found low density had a better thermal ride through with hot aisle containment. For their study, low density was defined as 7 kilowatts or less per cabinet. Typically, you will deploy hot aisle containment 1 pod at a time, though some containment vendors will now give you cabinet-sized filler panel that will allow you a little more flexibility there. And hot aisle containment is going to be compatible with row-based cooling. Cold aisle containment, the whole data center becomes the hot aisle, and that can be uncomfortable. The Intel T-System study showed us that for high-density cabinets, the thermal ride-through during cooling failure was statistically better. Their high density for that study was 17 kilowatts per cabinet. Cold aisle containment is going to usually be much better for a retrofit of an existing data center because the containment structures will be able to avoid all your overhead obstructions that could be your power distribution, your low voltage distribution trays or runway, lighting, or any other overhead obstructions. Cold aisle containment does create a separate volume for fire suppression, so you're basically going to have 2 parallel fire suppression systems, one for the overall room and then one that will address each of the containment areas. Again, this is typically deployed a pod at a time. Cold aisle containment is going to be sensitive to overpressurization. I refer you to a white paper available on the Tate Access Floors website on the ramifications of containment. And they found that with static pressures up to around 0.15 of an inch water column, that they were seeing up to 400 CFM bypass air forced through the servers and overpowering the server fans in these containment structures. So with cold aisle containment, it becomes a lot more important to have a good control system to manage the pressure differentials in the room. Again, cold aisle containment is going to be compatible with row-based cooling. Cabinet containment, you create a much more hospitable work environment, may be important where there's a lot of activity, may be less important for a lights out data center, obviously. Fire suppression, with 10-foot centers on sprinkler pipes, you'll only be able to get in 3 or 4 rows of cabinets before you're going to have a clearance issue with the cabinet chimneys. If you're on 8-foot centers, that fits in perfectly with a 16-foot pitch, and your fire suppression system will be just fine. Cabinet containment can be done on a raised floor for air delivery, but it can also work with any other kind of air delivery into the room, whether that's fan walls, overhead delivery, or some delivery system that's associated with a particular economizer or central cooling system. You build the data center 1 cabinet at a time. We found in our cabinet solutions that that will have about a 3,050 CFM density threshold. That density threshold we've determined by that point at which we add 0.05 of an inch head pressure to the server fan performance of the overall pressure head they're pushing against through the server chassis themselves. That 3,000 CFM will equate to anywhere from 19 kilowatts up to nearly 50 kilowatts, depending on the delta T of the server equipment, which is basically the fan efficiency of the server fan equipment. Again, the same flexibility with hot aisle containment is associated with cold aisle containment. So the rest of the presentation will be drawing specifically from the Thermal Guidelines for Data Processing Environments ASHRAE Handbook, the 3rd edition, which was just published 3 months ago, and specifically looking at Appendix C, which gives us a detailed flowchart for the use and application of ASHRAE data center classes. So this is how we can determine an optimum operating temperature for the data center that'll give us the best total cost of ownership, looking at acquisition costs and operating costs associated with our decisions. So just a quick reminder of the Class A1, Class A2, Class A3, and Class A4 server allowable operating temperature range juxtaposed on a psychrometric chart. And you can see the A3 and A4 servers consume most of the weather profiles that where most of our data centers are going to be living. The flowchart itself starts with the question we're trying to answer is how to reduce our total cost of ownership and take advantage of the higher operating temperatures from the different server classes. And there'll be a separate flowchart for new construction, a major retrofit, which sometimes called a brownfield construction project, and then an efficiency improvement project or giant Band-Aid, as it were, for an existing data center. And there's a detailed flowchart associated with each one of those 3 major categories. And as you work your way down those decision trees, you will encounter notes referring back to this note table that is worth just touching on, because these are main points of consideration for any one of these analyses. The first point basically gives us the importance of the containment. The absolute segregation between supply air and return air is required to reap the benefits of anything that we may be doing on either one of these 3 decision trees. Second point just basically reminds us that the data center has to operate to support the needs of the weakest link in the whole chain. So if 3/4 of our equipment is A4 servers, but we've got legacy equipment that has to operate at the A1 level, the data center must meet the needs of the A1 servers. The third point is we do want to consider at least one scenario without a chiller. And we want to consider the reliability impact on our equipment for the chillerless data center. And we'll look a little bit more about the implications of that in subsequent slides. The high temperatures referenced here in bullet 4 are probably not going to happen today, even if we're running A3 or A4 servers with inlet temperatures above 100 degrees. Most server fan profiles are going to ramp up and cap that exhaust temperature off around 131 degrees or 55 centigrade. In future generations with technology refreshes, though, we can expect these temperatures to creep up into the ranges of this warning level and to be sure that we have an environment where those temperatures are going to be okay. And then finally, we want to keep in mind that as we raise the temperatures, the server temperature sensing is going to respond to that, and there'll be at some point where we're going to be consuming more air through those servers, which means our air delivery system into the data center is going to need to ramp up accordingly. So there's basically a twofer there, a double whammy, when we start paying those fan penalties. And we'll talk a little more detail about that in a subsequent slide. So on each of these decision trees, there's going to be a point where you make a decision about you either have an economizer or you are going to plan to build an economizer for the data center. You answer yes or no. And regardless of the answer, you're going to end up in a block that's going to require you to do this total cost of an ownership analysis with or without the economization at various temperature levels. You're going to need to understand the reliability, availability, impact on your server equipment. You're going to need to understand the operating cost and capital budget impact of A3 and A4 servers, and you'll end up with being able to say, this is the temperature I want to operate my data center at, because it gives me the overall total lowest cost of ownership when I look at my capital budget and operating budget in combination. So before we begin the total cost of ownership analysis, we want to be sure we've got the upfront data required to make all this work. That's getting hourly temperature data for the location of our data center. You can buy that from a variety of sources, from anywhere from $15 to $30 a year. I suggest you get 5 to 7 years worth of data so you can exponentially smooth out any oddball years that might skew the study. We want to understand what our sensible cooling load is going to be. If this is an existing data center that we're doing an efficiency improvement project on, that's easy. That's the UPS output or our metered PDU or power strip readings. If it's a new data center, the best path is to go into the server manufacturer's online power calculators and come up with some estimates on what your IT heat load might ultimately be for this space. We want to understand our economizer operating costs and also have a capital budget for different economizer options as well. And finally, we want to understand the acquisition cost differences between Class 1 servers, Class 2 servers, the A3 servers, and the A4 servers. So you're going to want to have a data collection point for your studies. This is just an example of what that might be. I'm not going to go in detail over all these columns, but this presentation is available in the archive on the Graybar website. So I invite you to steal this chart or at least borrow some categories from it if you're planning to do this kind of an exercise. So what do we do once we get into the working part? The first thing is in that left-hand column, we're going to be putting in supply temperatures. And in the next column, we're going to be putting maximum inlet temperatures. Those can vary as little as 1 or 2 degrees between the two temperatures, up to maybe 15 degrees or more between the two temperatures, depending on the quality of containment. Those points can be discovered through computational fluid dynamics analysis. And this is a good place to interject that in your overall planning process. A1 servers will start consuming more energy with a steep increase on the fan performance curve above 77 degrees. A3 and A4 servers are going to kick in their fan energy penalty at higher temperatures. If you can't get that information from your server manufacturer, you can get it from charts in the ASHRAE handbook, and those charts, by the way, were developed by the server manufacturers, so that's defensible and accurate enough for planning purpose type information. For our capital plan considerations, obviously we need to consider the difference between the A1, A2, A3, and A4 servers. We want to look at the cost avoidance of eliminating the chiller plant altogether, so at least one scenario should drive down that path, if not more. Look at our economizer capital investment and also the operating cost for our economizer, and also look at the ASHRAE handbook best practices for datacom facilities energy efficiency that will give you a chart for your operating costs for chiller plants at different water temperatures, and that should go into this budget as well. Consider crack or craw capital avoidance. If you've got cooling coils that are integrated into your economizer, so the precision cooling units then would not need to be part of the capital plan. Your raised floor is going to cost significantly more than putting in a suspended ceiling, so those cost deltas should be a part of the plan. If we're doing waterside economization or evaporative cooling, or we're just going to replace the chiller completely with ambient water as our cooling and heat rejection method, then we may need larger water storage affecting capital budget. We may have higher evaporation rates, which will affect our operating budget. Our control system, we talked about cold aisle containment. You want to be sure you've got highly sensitive and accurate pressure sensing feedback system that will drive your air delivery performance into the data center. Our CRAW or economizer fan energy, and understand the how to calculate your cube effect affinity loss savings as you reduce those fan energy requirements with a good containment structure in the data center. Chiller energy at different leaving water temperatures, I said you can get that data either from the vendor or from a table out of the ASHRAE best practices for datacom facilities and energy efficiency. And the X factor, here you will want to go back to the ASHRAE handbook on the environmental guidelines, and this chapter will give you a way to look at the hours of operation and different temperature buckets for your data center, and the effect on the reliability of your equipment in the data center in comparison to the X point, which is operating the data center at 68 degrees 24/7 all year long. And you will find in one example, they looked at a data center in Chicago and actually found a 1% reliability improvement by following Mother Nature, allowing the 90-degree days, but also allowing the lower end of the allowable limit as well. And to put it in perspective, depending on how many servers you have in a data center, a 1% decrease in reliability may mean that results in one more server every 5 or 10 years that would require a reliability-based replacement. So those are just factors that need to be included into the overall budget. So to wrap up, the keys to success for performing this type of an analysis and driving to this type of plan: start with containment, utilize computational fluid dynamics to help set those initial planning temperature points, do at least one scenario without a chiller to see if that'll work, and it'll work for many more locations in the country than is often thought. And then just to be sure to map the trade-offs of A1 servers versus A3 servers, acquisition costs versus the operation costs. So that being said, questions that you could have typed into your comments. I believe Carl may have already collected some, so I'll entertain those now.
Ian, we do have some questions, and we want to thank you very much for your presentation. For those that are online with us today, you can type your questions into the question box at the bottom of your screen or wherever it may be located on your screen, and go ahead and send them our way, and we'll get to those. We'll go through them. We have about 10 minutes left of time that we can do that. Any questions that we don't get to, you'll get an email from us with the answers to your question. We'll get in touch with Ian, and we'll make sure we respond to any questions you have. But you have to type it in so we can get it. So anyway, we'll start our Q&A right now. And Greg asked this question. It came in earlier in your presentation, Ian, when you were talking about how high the temperatures could be approaching in the next few years in the hot aisle. And I think the presentation mentioned they could be approaching in our future 140 to 160 degrees Fahrenheit. And so Greg asked this question: what is known about the effects of high heat on data cable, fiber, individual power supplies, and also possibly cabinet PDUs? Has this been looked at about the high temperatures and the effects on the equipment that might be on the hot side?
Yeah, that's a very good question. In fiber, and I'm not sure about when we get up to 140 or 160, but I've talked to fiber manufacturers, and when we get up to the 55 to 60 centigrade, which is 130 to 140 range, that there's not any derating in fiber. For copper, you're going to start derating your speeds or the capacity of copper when we start getting up into the 50 to 55 centigrade type area. So that's that copper is an issue. With PDUs, most PDU manufacturers now are offering at least one SKU that is intended to operate at higher temperatures, and that's a spec that you need to look for going forward if you're going to take advantage of these kind of economizers or economies that you're speccing PDUs that will operate in those temperature ranges. There's also going to be a slight derating on your power cords as well, but that doesn't really kick in until we get up around 55C, and the derating curve tends to be slight enough that if the PDUs themselves are rated for those temperatures, that's not an issue.
Great.
But you need to pay attention to that.
Thank you for answering that, Ian. And another question that I had, and again, I want to remind anybody that's online, if you'd like to ask a question, just type it into the appropriate area on your screen and send it our way, and we'll get to it. But what's your experience with customers adopting the new ASHRAE guidelines? When you travel around the country, Ian, and visit with data center operators, owners, facilities people, are we seeing people raising their set points? Are we moving toward this new ASHRAE guideline? Are people adopting it, or are we still a little reluctant to move the temperatures up?
The answer is kind of, sort of. The first big change is making the switch from a set point to a supply temperature set. And we're seeing more and more people now who are making that change. And when they make that change, the immediate result is the supply temperature is increasing from somewhere in the low to mid 50s up into the mid to upper 60s. So that's a long way still from taking full advantage of the ASHRAE envelope, but that's progress that I'm seeing on a pretty large scale now. Not the majority yet by any means, but that's being adopted. And from there, folks just tend to go 1 degree at a time, for a couple months and just to see what happens. And I think the industry is approaching it with that kind of caution.
Pedro asked this question, Ian. What's the max kilowatt per cabinet for each of the containment options, assuming there's no in-row cooling? So do we know what the maximum per cabinet is for hot aisle contained or cold aisle contained, or for chimneys, assuming there's no row cooling?
Yeah, the kilowatt rating is only a derivative number because the gating item is going to be the ability to move air. And so we know with chimney cabinets that we can move 3,050 CFM through an individual cabinet without affecting server fan performance or without any thermal effect, assuming that it's a cabinet that's been optimized for that separation. That 3,050 CFM for a pizza box server is probably about 19 kilowatts per cabinet. That 3,050 CFM for your typical blade server is going to be 30 to 35 kilowatts per cabinet. That 3,000 CFM for what we call a supercomputer or HPC optimized blade system, that's going to be 40 to 50 kilowatts per cabinet. It just depends on the CFM per kilowatt ratio or delta T of that equipment. For hot aisle containment and cold aisle containment, those numbers will just increase from there because the space into which you're creating a pressure profile is going to be that much larger than that space that's just in the rear of the cabinet.
Charles would like to know about the operating temperature of equipment. Is it measured at the air intake of the equipment, or is it measured at the fan discharge side? Where do we measure that operating temperature of equipment?
That's at the air intake.
At the air intake. Okay. One more question I have, Ian, and we'll wait and see if we got any more that come in, is, again, as you're traveling around and visiting with data center owners and operators, what are you seeing with new data center construction? Are we seeing a movement toward on-grade type construction with no raised floor, or are people still using raised floors? What's your experience been as you visit with customers when you travel around and they're redesigning and rebuilding their data center?
Well, there seems to be a real move away from raised floors. I think raised floors, again, are still a predominant architecture, but much less so. And I hear more and more people now talking about their next design will not be a raised floor, or their current plan is not a raised floor. So that's definitely a trend.
Okay. Sean asked this question. Have there been enough different data center scenarios documented that a company looking at designing a new data center can find a study that looks similar to their data center plans, thereby getting a good starting point for their own design. Do you know of a documentation that shows different types of data center design scenarios and they're kind of collected together? Ian, does that exist?
Yeah, but unfortunately I can't answer that question off the top of my head. I have seen something like that in one of the data-centric e-newsletters that I subscribe to, and I believe I have actually archived that somewhere, but I can't remember the author or the title or anything, so that would require me to do a double check.
All right. That's great. And so, Sean, just so you know, we're not going to leave you hanging there. Ian and I will get together, and we'll send you an email. And when Ian gets into looking in his archive, we'll go ahead and respond to that. One last question, and then we're going to have to go here. We're running out of time. Pedro asked this question too. You had mentioned one of the containment options was compatible with in-row cooling. Which one was it, and why are there other options not compatible?
Well, no, actually both cold aisle containment and hot aisle containment are compatible with in-row cooling.
Right.
And
great.
Your cabinet containment is obviously not going to be, because it's directing the hot air away from recirculating it through the in-row coils.
All right. Well, again, Ian, we want to thank you so much for your time that you spent with us today. Your presentation was just absolutely outstanding. The information was very informative. We can tell that by the questions that are coming in. If you didn't get your question answered, go ahead and type it in. We will get with you via email and respond to your question, even though we didn't mention your question online. Remember, look in your email. If you were one of the first 50 folks up on this thing and stayed for the seminar, you'll get a webinar. You'll get a certificate for a cup of coffee. If you would like to have a conversation with Ian, and we can help you connect you up with the cooling experts and subject matter experts at CPI, just get in touch with one of the Graybar sales representatives in your area, and we'll be glad to connect you up with Ian and the people on his team that are true experts when it comes to cooling inside the data center. So again, Ian, thank you very much for your time. Thanks everybody for attending. Y'all have a great day.